Hey everyone, welcome back. This will be lecture B of lecture 12B, part B of lecture 12. And so we just finished discussing arc length, how to use integration to find the length of an arc. And now what we want to do is we want to switch over to how to use integration to find the surface area of a surface of revolution. Okay, a surface of revolution. So what is a surface of resolution of I'll probably make that mistake a million times. A surface of revolution. Right, a surface of revolution. What is it? So if the graph of a continuous function is revolved about a line, okay, the resulting surface is a surface of revolution. Okay, so that's kind of the definition here, but what does that mean? Well, let's say we've got some line L and I spin it around an axis. Then what I get is a surface of revolution, namely this part here, right? There's a surface area that's spun out by this line L. Okay, so this shape here that we're looking at is frequently referred to as a frustum. Okay, and basically a frustum is just, you can think of it as just a geometric solid that is sliced by two parallel surfaces, right? And so basically this end here has been sliced off, and in a parallel fashion the other end has as well. Okay, so that's what we mean by a frustum. Now if we wanted to find the surface area of this figure, if you were to roll this out, it might look like, it might look something like this, possibly, right? So it's going to have, some circumference on this end, which is going to be of a certain length, and then over here it's going to have some other circumference, which is going to be of a certain length, but certainly longer, and then there's going to be two lines connecting it. Okay. And so if we were to roll this out, it would look like this, and this is obviously a trapezoid. And so we know how to find the area of a trapezoid, and that is what our formula, our integral technique for finding surface area in general is going to be based on, right? So the surface area, the area of this trapezoid, is basically going to be this length A plus this length B divided by 2. So you add those two together, and then you multiply by the height. And that's the area of the trapezoid. Okay, we're going to do something a little bit different over here, but it's going to be based on this formula. So we're going to think of, right, you've got the axis of revolution, right? And then there's going to be a radius here, which we can call R1. And there's going to be a radius down here, which we could call R2. They're obviously different, right? Okay. Now, this circumference here would be 2 pi R1. This circumference over here would be 2 pi R2. Okay, if we add those two together, multiplied by the height, and divide by 2, then this is what we got, right? That's this formula. 2 pi r1 is going to be the length of this circular part here, which is this. 2 pi r1, sorry, 2 pi r2 would be this one. 2 pi r1 would be this one, which would be the length of this circular region here, which would be this. Divide by 2 and multiply by h, and you get this. Right, so we can rework this a little bit, and we're going to need to. So I'm going to pull the 2 pi h out to the front, and then I'm going to leave r1 plus r2, and then all divided by 2. You may be saying, why are you not canceling those 2's? Well, what I want to do instead of canceling the 2's is I want to think about r1 plus r2 over 2. So we can kind of think of, I mean, basically r1 plus r2 divided by 2 is the average radius, right? So kind of depending on, where who's teaching you about trapezoids, some people will outright state that this is an average calculation here. You're taking the average of the two. Others will tend to think of it as something different, but it really is kind of the average, right? And what we're doing here when we do r1 plus r2 over 2 is explicitly calculating the average of these two numbers and using that. And so what I want to do instead of canceling the 2's is I want to say let r equal r1 plus r2 over 2. Okay, so if I do that, then this becomes 2 pi h times r, right? Where r is this average value. Okay. Perfect. All right. So, and one other thing here, right? So instead of h, right? H is kind of the trapezoid concept. Over here, what should the h be? Over here, h is this L, right? It's this would be your h, right? It's the distance between the two parallel sides. So over here, L is going to be the distance between the two parallel surfaces. Okay, and so letting r equal L, the area is equal to 2 pi L times r. Okay, so this is going to be, this is the basis for our surface area calculation. This will be the basis for our surface area integral. Okay. All right, so let's go ahead and break it down. Okay. So let's draw a picture, and then we'll do this breakdown. So I've got some curve in here. Okay. And we're going to define delta. We're going to let delta be a partition where a is equal to x0, which is less than x1, less than ... less than xn equals b. Okay, so that means I've got an a equals x0 somewhere in here, and I've got a b equals xn somewhere out here. Okay, and so you can see that that's going to correspond to the endpoints, right? And so these are basically giving us the parallel surfaces for this frustum shape here. Okay, so you can imagine this is going to be our axis of rotation, right? So this is going to get rotated around here, and it's going to sweep out some kind of a shape. Right, let's just draw what we think it might look like. Let's see if we can, how bad we can do this. These are harder to draw than you might think. So it might look something like this. No, that's not actually too bad. Okay. All right, so then what's the idea here? Well, so what we're going to do is on this shape here, there's going to be a delta Li, right? And that's, well, first I guess we need our xi minus 1 and our xi, right? So here's our ith interval, kind of our representative interval. And we've got this delta Li, okay? And delta Li is going to be the length of this line here. So we just got done talking about arc length, right? So we're going to let delta Li, so that's obviously going to come into play here. Delta Li is going to be our arc length. And it's going to be equal to, we know delta xi squared plus delta yi squared, and then the square root, right? That's the length of this line here. It's an approximation of the length. Actually, it's a straight line length, but that's what delta Li is going to be. Okay. So the line segment of that has this length is going to basically generate a frustrum, pretty much like the previous example that we saw. So let's write this down. When this is rotated, just this segment here, when this Li segment, this ith interval segment is rotated, we will get a frustrum like we saw previously. Okay, so like this guy here. I remember this figure here. Okay. All right. So let me just really quickly redraw it here. So here's your Li, and then here you've got your R1, there's your smaller R2, axis of rotation. That's what you're going to get, right? When you flip this around the x-axis here, it's going to sweep out some kind of an area here. And this is going to be a straight line. Okay. Okay, so we'll let, so in our previous example, we saw how instead of R1 and R2, we're just going to have an R. So we'll let Ri be, you know, the average radius of this frustrum. Okay. So if that's the case, then by the intermediate value theorem. So what does that mean? So it means that your Ri is going to be somewhere between R1 and R2, right? It's going to be somewhere in this range. Okay, so maybe it's like right there. I'm just eyeballing it. But by the intermediate value theorem, so another call back to calculus 1. By the intermediate value theorem, there exists a di, right? A di in the interval xi minus 1 to xi, such that this little Ri, this average radius, right, average height up above here, will be equal to f of di. Okay. Now, okay, we got to make this clear. This is, this can be a little bit of a tricky construction, right? So this is like our Ri, our R1, sorry. This is like our R2. Okay. Somewhere in the middle is the average. We'll call it R. Right? That means there's a di here such that this is f of di. Okay. That's all it's saying. This is actually very intuitive, rather obvious actually when you kind of break it down and kind of get outside of the formalism a little bit. Right? But you've got some height here, you got some height here. There's an average of those two. It's going to be some value on the function. There's a di for that value. Right? This is a smooth continuous function. There's no holes or gaps or anything, so that di must exist by the intermediate value theorem. Okay? That's all that's being said here. Okay. And so we've got Ri equals f of di. Okay. So then the lateral, we'll call it the lateral surface area. Okay. Right, the lateral surface area of this delta Si on this ith interval can be written as what can we write it as? Well, it's delta SI will be equal to 2 pi r of I times delta Li. Okay, right, so this is 2 pi times the radius times the height. You can think of that. We've just substituted in this Ri and this delta Li because we're talking about the ith interval. Okay, so this is what we're starting with. And so that's equal to 2 pi. Now instead of Ri, let's put that f of di in. And instead of delta Li, let's pull in our xi and our yi. Okay, so delta Li would be, this would be the square root of delta xi squared plus delta yi squared, like so. Okay, and then this piece here, we can do the exact same trick that we did in part A of this lecture, right? When we were talking about the arc length, we had this long sort of algebraic trick that we employed here, but basically we can turn this into 1 plus delta yi over delta xi squared times delta xi. Okay, you may remember that trick. If you didn't watch the previous part of this lecture, then you're probably in the dark, but basically you can multiply this term top and bottom by delta xi over delta xi squared, right? Delta xi squared over delta xi squared, and then when you can rearrange it and do some algebra, and the whole thing can be rewritten like this. Okay. All right. So then, similar again to what we talked about in the previous lecture, there's going to be the mean value theorem is going to come into play here. Right, so mean value theorem basically says there exists a CI on the interval, CI in xi minus 1 to xi, that's an I, right, a CI such that f prime of CI is equal to, you know, f of xi minus f of xi minus 1 over xi minus xi minus 1. Okay, and so this is going to be equal to, you know, delta yi. That's just what this is. This is yi minus 1 basically. So delta yi, and then this of course is delta xi on the bottom. Okay, so given that, we can finally say that our delta SI is equal to 2 pi f of di, so this is stuff we all had before, times the square root of 1 plus, now instead of, you know, what we saw here, delta yi squared over delta xi squared, let's plug in this instead. Right, so these two are equal, so let's use this instead. So it'll be plus f prime of ci. We do still have to square that. Okay, and then it's again delta xi out here. Okay, so this is going to give us, this is a nice concise formula, relatively concise formula for the surface area of the particular frustum that we're looking at, for the particular representative rectangle that gets rotated, right? It's going to give us the outer surface area. Well, so we can obviously sum over all such intervals, and this is what we always do, right? So S is approximately equal to this, the sum, well, we'll put the 2 pi outside, sum of I equals 1 up to n of f of di times 1 plus f prime of ci squared, square root of all that, times delta xi. Okay, so that's basically going to give, this is the approximation for the surface area. Now, of course, this is an approximation and an increasingly accurate approximation. So letting the norm go to 0 and go to infinity, this becomes the integral. Right, so letting the norm of the partition go to 0 and the number of the partitions go to infinity, this becomes right, so it becomes, of course, it's just that thing with the limit notation on the front, and it becomes the integral from a to b, well, 2 pi times the integral from a to b of this f of x times the square root of 1 plus f prime of ci. Okay, so there we go. All right, so something to note here is that this f of x here, this f of x is frequently written as r of x, and just to kind of makes things a slightly less confusing. Okay, let's do an example. Let's try an example here. We've got 2 examples in mind to do. Okay, so the first one, find the area of the surface formed by revolving the graph of y equals x cubed on the interval 0 to 1 about the x-axis. Okay. All right, so as per always, start with a picture. Okay, so we're looking at y equals x cubed, and we're specifically looking at it on just the interval from 0 up to 1. Okay, and so kind of comes up like this over that interval. It's got a little bit of a lip here at the end, like it's flattening out. Okay, and this is 1, and this is also 1. Okay, so you can imagine what this might look like if it was spun about the x-axis, right? It's coming around like this. It would kind of look like this. This is maybe an exaggeration, but you know, it'd have some kind of a look a bit like that, wouldn't it? Okay, and so what is our r of x? Right, what's the r of x here? Let's write the formula down. So s here is equal to, what are we all looking for? The integral from a to b, and then there's this rx out front, which is the radius function, and then there's the square root of 1 plus f prime of x. And we gotta square that. Okay, so it looks like that. So where's the rx here? Well, rx is going to be the distance from the axis of rotation along the parallel surfaces of the frustum, right? So this is our rx, right? So in this case, and this isn't always the case, in this case rx equals f of x. Okay, it doesn't always. Okay, in this example it does, right? So rx is the x cubed. Okay, and then we just need the f prime of, so we know the limits, the interval are, you know, from surface area to parallel surface to parallel surface. It's going to be 0 up to 1, so a and b are 0 to 1. We need the derivative that's pretty easy to find, right? It's the derivative of x cubed, so it's just 3x squared. Okay, so we have the three pieces that we need to plug in here, and they all make sense. And so let's do this integral quick. So s equals 2 pi, and it's the integral from 0 up to 1, and rx we said was x cubed, and then it's the square root of 1 plus f prime of x squared, which was 3x squared. So we need to square that, just like so. Okay. And, perfect, this is 2 pi, 0 to 1, and we can write this as x cubed times the square root of 1 plus 9x to the 4th. Okay. And we might want to, get rid of the radicand and just kind of do this, get rid of the radical and write it like this, right? Okay, of course, that's optional. So can we do this integral? Well, let's mess around here. If we let u equal 1 plus 9x to the 4th, right? Because you can see you've got an x to the 4th and an x cubed, so change of variables is very likely to work here. And that means du is equal to 36x cubed. Okay, so that looks pretty good. We've got the x cubed, we don't have the 36, but we can just write du over 36 equals x cubed dx. Sorry, there should be a dx there. Okay, so this is kind of the side calculation, just to make sure you understand what the change of variables need to be. And so this is 2 pi times, well, you're going to have to bring in a 36 here, aren't you? So 1 plus 9x to the 4th, and then 36. Dang. So it's 2 pi over 36, and then it's 0 up to 1. And then just kind of rearranging these things. 1 plus 9x to the 4th, and then x cubed, but I've multiplied and divided by 36, right? To get this change of variables to work. Okay, like so. So this is... And so then this is our u, and this is our du. Right? Yeah, perfect. So I get 2 pi over 36 times the integral from 0 to 1 of u to the 1/2. This should be the 1/2 power there too. Du. Perfect. All right. Then just do the integration here. All right. So this would be u to the 3/2 over 3/2. 0 up to 1. And that means we get, let's see, so this should be pi over 18 outside here, and then it's 2u to the 3/2 over 3 from 0 up to 1, and so this would be pi over 27, and then it's u to the 3/2, but let's put in our other thing, 1 plus 9x to the 4th. Just like so. Okay. And perfect. We can evaluate this pretty easily, I bet. So it'll be pi over 27, and then 1 plus 9. So this is just 1 and 0, so that's why this is not going to be too bad. So we've got 1 to the 4th is 1, so 1 plus 9 is 10. So this is 10 to the 3/2. And then minus, plugging in a 0, it'll be just 1 to the 3/2. So let's see, pi over 27 times 10 to the 3/2 minus 1. That's probably about as good as it's going to get. And so I'll let you plug this in for the approximate value. Actually, maybe I have it somewhere here. Yep, I do. Actually, yeah. No, yep, I do. 3.56 approximately. Okay, so that's the approximate surface area. This is the precise surface area, this is the approximate surface area of this figure that we drew here. So this is the surface area of this part, right? Right, remember, presumably this thing is hollow, okay? So we're only interested in the surface area. Well, it doesn't matter if we can't really say if it's hollow or not. It's not really, but it's you know, we're really just rotating a line. We're not even thinking about this as a region. We're rotating just a line. So it's just spinning out this line in space. It's sweeping out this, you know, surface. Okay, how about we do one more example? Okay, one more example. Let's find the area of the surface formed by revolving the graph of f of x equals x squared on the interval 0 to the square root of 2 about the y-axis. Okay, so let's draw this so we can get everything kind of straight. All right, so we know what this looks like. This is just the x squared function. So somewhere up here we've got a 2, and that's going to correspond to the square root of 2 down here. So we're interested in this interval, and this time we're going to rotate it around the y-axis. Okay, so remember our integral looks like this. S equals 2 pi times the integral. In this case, well, I'll just put a to b. A to b times r of x times the square root of 1 plus f prime of x squared. Okay, so this is our formulation here. And so what is our r of x? Right, what is this piece? Well, remember, r of x is the average radius between, you know, the surface itself and the axis of rotation. So it's going to be this. And what is that? Well, it's just some distance on the x-axis, isn't it? Okay, up at the top it's going to be square root of 2. At the very bottom it's going to be 0, and everything in between is everything in between. Okay, so Rx in this case is x. F of x, of course, is x squared. So Rx is x. F prime of x is going to be d/dx of x squared, which is 2x. Okay, so we've got that. So we can plug and chug here. So s is equal to 2 pi times the integral from 0 up to the square root of 2. So integrating along here. And it's going to be x times the square root of 1 plus 2x. And we have to square that. Take the square root. Just like so, right? Okie doke. And let's see here. This is 2 pi integral 0 to square root of 2. And so in here we've got the x, and then we've got 1 plus 4x squared. 1/2 power dx. Okay, no problem. Let's go ahead and do the u substitution. So we'll let u equal 1 plus 4x squared. Then du is equal to 8x dx. Okay, so we don't have the 8 here, but we have the x, and so that's not a problem. We can just multiply and divide by 8. So we get 2 pi over 8 times the integral of 0 to the square root of 2. And then it's 1 plus 4x squared, square root of that, times 8x dx, right? So that's all you need to do your substitution here. So integral from 0 up to the square root of 2, and then it's u to the 1/2 du. And just like we've seen previously, this will be pi over 4, and then this will be u to the 3/2 over 3/2, and 0 up to the square root of 2. And so that means this is pi over 6 times, now u, remember, is 1 plus 4x squared. And this is the 3/2 power. Okay, and so finally, what do we get? Well, yeah, if we plug in the square root of 2 here, we get square root of 2 squared, so it's 1 plus 8, so it's 9 to the 3/2 power. And then we got to do the same thing for 0. So you plug in a 0, you get a 0 there, so it's just 1 to the 3/2 power, so minus 1. And this one actually we can probably figure out precisely because 9 is a square. So the square root of 9 is 3. So that's 9 to the 1/2 power is 3. And then 3 cubed is 3 times 3 is 9 times 3 is 27. So this would be 27 minus 1. So 26 pi over 6, which is 13 pi over 3. Perfect. Okay, there we go. So that's a couple of good examples of how to calculate the surface area of a surface of revolution. Okay, so I think we'll leave it there, and we'll carry on with an application from physics in our next lecture. We'll talk about work. We'll talk about what work means in physics. All right, see you then.